So far, we've been lucky in the sense that the problem we're trying to solve is specified in a recursive manner up front. But sometimes we have to dig a little bit to find the recursive structure in a problem. It's not explicitly stated as part of the problem, and we're looking for a kind of puzzle solution to a larger problem in terms of solving it by a smaller version of the same problem. So with most students, this is a bit of a concern because you're relying on the code you haven't yet written to solve a problem. But if you have faith that it's going to work, and if you can see the recursive substructure, then you will get a solution and it really will work. So as an example, let's take a look at sum of n, which you can see here as a formula, the sum of all the integers from 0 to n. And what I recommend you think of is that sum is just a box that, given its parameter n, spits out 0 plus 1 plus and so on up to and including n. So if I were to feed sum a green ball, which is a strange thing to feed it, it would just spit out 0 plus 1 and so on up to and including the green ball. We're so used to looking at these symbols as mathematical symbols, but for once, I really would like you to see them just simply as text, that sum has this ability to spit out the text that you see before you. Now, if we look at sum of n, and let's take an example, say sum of 4, whose expansion we see here, if we really believe that sum of n does its job, then the question to ask is, if we give sum the value x, it would produce 0 up to and including x. Sum of x plus 9, we start at 0 and end up at x plus 9. Whatever value we put into the parentheses is the thing that shows up on the very right of the expanded expression. So if we look at sum of 4 and see it as 0 plus 1 plus 2 plus 3 plus 4, the question to ask ourselves is, where in that expression do we see the next smallest example of the sum operation? And it turns out it's 0 through 3. So if 0 through 4 is the big problem, 0 through 3 is a slightly smaller example of sum. And if I trust that sum of n will really do its job, then I could compute sum of 4 by computing sum of 3 and then simply adding a 4 to it. So mathematically, the sum from 0 to 3 is exactly the same as calling sum and passing it a 3. As a spitter out of text, sum would emit 0 plus 1 plus 2 all the way up to plus 3. So I can simply substitute 0 through 3 as a sum by a method called a sum of 3. And I now have a recursive specification, sum of 4 is equal to sum of 3 plus 4. The ability to write it that way required finding the next smallest example of sum. Let's look at this more generally. So let's look at sum of n, which is the sum of 0 through n. And here you see the sum expanded out a bit. Where in here is the next smallest example of the sum operation? It's the sum of everything up to and including n minus 1. If only we had an answer to that, then we could simply take that and add n to it to get the answer. Now, if we really believe that sum of n minus 1 would do its job and generate the highlighted sum shown here, then we can simply substitute it and say sum of n is equal to sum of n minus 1 plus n. We don't really have to think about how this is being computed. We just have to see sum as a textual substitution of its expansion for sum of n minus 1. And this gives us an explicitly recursive formula, and then we're back in the domain we had before where we just have to code it up as written. The only thing missing is a base case. We can't go on forever computing sum of n in terms of sum of n minus 1. So the last thing we have to think about is what's the smallest example of any sum. And we might say, well, sum of 0 is the smallest example, and we simply define that as 0. So this formulation leads to what you see here, namely sum of n is 0 if n is 0, and otherwise it's the recursive specification we developed by finding the recursive substructure. Sum of n is sum of n minus 1 plus n. And that leads directly to the code you see here. It's a simple transcription from formula to code, and that's a correct solution for sum of n. Now what I'd like to do is consider other possible substructures that don't lead to a successful solution. So for example, if we started with the sum going from 0 to n, we might have said, well, maybe the next smallest example starts from 1 and goes to n, as highlighted here. But if I believe that's the case, how do I express that in terms of sum? The boxed expression is sum of n minus 0, which leads to the expansion sum of n is 0 plus sum of n minus 0. The zeros cancel. It's true mathematically, sum of n is sum of n, but this doesn't involve a smaller example of the larger problem. And so it doesn't lead to a recursive solution. So to work, we must find a smaller instance of the function, one that seems slightly easier to compute. And the less distance between the bigger problem and the smaller problem, the easier it'll be to code up the solution. And that smaller problem has to point us in the direction of the base case. We went from n to n minus 1, and that's a diminishing of n, and our base case was all the way down at 0. So going from n to n minus 1 is pointing us in the direction of the base case. Once we've identified the recursive substructure in the base case, we have a recursive formula that we can simply code as we did before.